everybody. Today I'm going to be covering the integral test, which is a topic in AP Calculus BC or Calculus 3. It's covered in Unit 9 of Unit 10 of AP Calculus BC in series and sequences and infinite series, I believe is the name. So we're going to get right into the topic of the integral test. So let's say I have a series. The series of n equals 1 to infinity of 1 over n. Some of you may know this as the harmonic series, and you know that the harmonic series is divergent. Well, we're going to use that knowledge and keep that at the back of your head, that you know that this is divergent. We're going to try to find out, and the integral test, what it does, it tests for convergence or divergence. And we're going to basically see if the integral test gives us this as divergent. So first of all, the integral test has two conditions. Is it positive? Meaning that all the values are above 0. And is it decreasing? Alright, so those are the two conditions we need to meet. So positive, from n equals 1 to infinity, will 1 over n be positive? Well, yes, it will. 1 over 1 is going to be positive 1. And if you take a really large, obscure number like 1 over 500 million, you're going to get some extremely small value, but it's still going to be a positive value. So therefore, it does check off positive. Decreasing. Is it always decreasing? Well, it is. We have 1 over 1 plus 1 over 2, if we just write the first few terms, and then 1 over 4, and it keeps on going, should mention. And you'll notice that it decreases. 1 over 1 is just 1, 1 over 2 is 0.5, 0.0333 repeating, 0.25, it keeps on decreasing. So it does meet both of the conditions, meaning that we can use the integral test to check whether this is convergent or divergent. Alright, so what do we do with the integral test? So first of all, you might guess we need an integral. And we're going to need something called an improper integral, which I covered in an earlier video, which I'll put in a card above, put in the description as well. So what an improper integral is basically just one or more of the bounds goes to infinity. In this case, you just need one. And so then we write 1 over x dx. So, and 1 over x is just going to be basically what we had here. So let's say we could have written this as, let's say, a of n. And here is basically just going to be a of x. Pretty much just a different variable, if you really want to think of it that way. You could use both n, but typically it's discouraged to use n here. So we have the integral from 1 to infinity, 1 over x dx. So we're going to try to solve this integral. So, as you guys might know, the antiderivative of 1 over x is, so if I just write this here, is equal to ln of x plus c. So that's the antiderivative. Oh, sorry, dx. I forget that too. So that's that. And since it's a definite integral, we do not need to worry about the plus c, since it'll cancel out. So we have ln of, and actually I'll do that in just a bit, minus ln of 1. And so an improper integral, basically what you need to do is you take n here, and you take this to the limit of n approaches infinity. You get the same thing because you have ln, or natural log of n, and as n approaches infinity, so basically you get the same thing right here, because you plug that in, you'll get whatever it is. And if you want more clarification on why I did this step, watch my improper integrals video for more clarification. So basically we can solve this here, and I'm going to go from this side. So ln of 1 is just 0. And ln of n, as n approaches infinity, is going to be, it is just going to be infinity, actually. Because if you guys don't know, I'm gonna draw a little mini version of the graph ln of n here. So it goes something like this. This is the graph of ln of x. So we got x, we got y. Sorry, that looks like an x. We got y. And so when you have x and y, then you have infinity. It goes to infinity because it keeps on going, and goes on forever. And that means we have here infinity minus 0, which is just infinity, meaning that the integral is divergent. And depending on what the integral is, or sorry, not the integral, the function is divergent. And that means that also the series will be divergent. Basically, if this integral is divergent, then the series will also be divergent. So then, in total, we find out, proving our confirmation, that the series 1 over n is divergent.